tell you about live video understanding at Twitter, the work we've been doing. So I'm not going to be exhaustive. I'm just going to focus on like two specific use cases. So people, I mean, maybe you don't know, but we have a strong and growing live video offer at Twitter. Twitter has acquired Periscope some time ago, which is a live streaming platform. And also you have like a live video, native live video coming on Twitter. I don't know if you've seen, but for example, Wimbledon has been starting to play live on Twitter. The NFL in the US is going to come next. And you know, there's a whole like, that whole offer is growing right now on the platform. So, but first I would like to tell you quickly about the mission we have in the AI group at Twitter. So it's called the Cortex group, so it's Twitter Cortex. And I'm just going to go quickly over like what we're supposed to do at Twitter in general, and then I'm going to dive more into live video specific examples. So yeah, one of the most important things at Twitter is user protection. The reason for that is Twitter is super open. Everybody can talk to anybody, you can mention anybody in your tweets and so on. So there have been a lot of stories about like, abuse or aggressive behavior or tweeting towards some people. So in this context, Twitter definitely wants to protect its users. So one thing we do at Cortex is building algorithms based on deep learning or not, but this is better in general, to filter sensitive content. So meaning on text, audio, video, any kind of content. So this is the first mission. It's usually tackled by classic classification models. So there's nothing super fancy here. The second thing is content understanding. The thing with that is we want to understand what people do, I mean what people post, just in terms of content on the platform. The reason for that is once you understand the distribution of content on Twitter or on your social network in general, you're able to build better products because you're able to modify the input distribution of your content, like on text, audio, video and stuff, and you're able to output a different distribution of content. So let's say you have like, on the live streaming example, you have like tons of selfies, right? People streaming themselves. And you have a very small portion of, I don't know, like concerts, talks, stuff like that. You want to be able to take that distribution of like maybe 90% of feeds and transform that into something that's globally more relevant for everybody. So yeah, so this is our job at Cortex, to make sense of the content, meaning we have to work on the taxonomy, we have to work on the tools to do that, and we have to work alongside the internal teams at Twitter to build that. So a quick example is like, here you have like 2 mosaics of Periscope streams. So you can see they're like classified broadly as outdoor scenes and animals. Just a quick example of simple stuff you can do to understand the content. So the third mission we have, and that's actually becoming more complex, is content indexing. So everything exists on Twitter. As you all know, everything is real time. I mean, it happens like super fast and yeah, all over the world. So ideally, what we would love to do is being able to search all the content there is on Twitter exhaustively and live, right? So it's a dream, but that means we have to index all types of input, meaning like text. So text is pretty easy to index, but then you have to index also images, videos, and even users, so that they are searchable in real time. So one of our missions is actually to build the indexing algorithms and to build also the search algorithms so that it happens super fast. So one example of that would be captioning, for example. So like you describe the scene, and then you can index by like the actual words in the sentence or actual like sequence of words in the sentence. The first mission we have is content relevance. What I mean by that is all the users have different tastes, they belong to different communities. Usually, I guess all the people in this room belong to like the deep learning community somehow. I mean, if you have a Twitter account, and that means you will have at least that taste, which is, oh, okay, I like deep learning, I like to have info about deep learning and all that stuff. And maybe you have like 2 or 3 or 4 other strong interests that you like. So one of our job is to project the whole input, right? The whole super dimensional input of Twitter live to each individual hypercube of interest, the best possible. That means we have to do like joint modeling on video, audio, text, and users. So yeah, and this is one of our missions as well. And it's probably the most complex thing for us. So the way we work at Cortex is we have like a very vertical environment compared to different other like companies. We can have like a more flat structure. So we have a research team, an applied research team, and then a product team. And basically the research team is going to feed the applied research team with new models and like ways of doing things. Then the applied research team is going to experiment on that and feed the product team with new experiments. Like, okay, I've tried with these parameters, I've changed a little bit the architecture of the model and so on. And then the product team is gonna feed Twitter. So when I say Twitter, it's like all the other teams with actual prototypes. Prototypes meaning demonstrations, but also like what is the performance in that case. And so, given the feedback from the actual teams, like external teams, we backpropagate the error and we say, hey man, it's not that good. And then we say, okay, we have to run another experiment. And then they get, okay, your algorithm sucks. So basically, the research team takes everything off, and everybody gets there. Oh, it's not my fault. Okay, so the Cortex focus. So that's what we want to focus on, and how we actually delimit the thing we want to do. Of course, we want to have fast prototyping for research. We want to be able to build new stuff very quickly, so we want to have the software stack to do that. We don't want to live in a super difficult to change way. So when we build new algorithms, we need that. Everything. I mean, it's all built on top of Torch, right? For those who don't know. We build a lot of tools around that. I'm going to talk about that a bit later. We of course need super large-scale clusters for experimentation. So thanks to our good friends of NVIDIA, we are able to train on multiple GPUs, super fast, and so on for training purposes. But also, we need to spend a lot of time working on taxonomies with the actual clients. And one last thing that's extremely important is once you have a model that's running, you have good results. It's just like a Lua script that calls like different libraries. You want to be able to embed that into a production environment as fast as possible, right? Because the product changes all the time. You have to adapt super quickly. So the way we do that is that we embed Torch in a Scala wrapper, and we actually just ship that, so you can use the exact same model, and we just have low-level GNI interface to deal with the communication. Low latency, of course, so that's a super important thing for us because we want everything to be live, and when we're talking about live video, it's not that easy. You cannot run live video classification on CPU. It's not because we could like spawn thousands, tens of thousands of machines, but it's not enough because the latency would be too high. So we deployed a GPU cluster specifically for inference, NVIDIA, of course. And the last thing we work on and we focus on is the whole software stack to make deep learning available at Twitter. So now I'm going to focus on the actual live video product. So the product needs usually that don't match the classic problems like the toy problems you see in the literature. ImageNet, for example, nobody actually uses ImageNet classes or like that kind of taxonomies. The product can change pretty quickly and we need to adapt. And each individual product on live video has its own requirements. So for example, take the highlights product. Highlights means you have a stream that can last from a few seconds to a few hours, a few days maybe, and you need to be able to recognize what are the most important parts of your stream. So that's a very specific problem, and you don't have the same needs for that you have for live video classification, for example. La video classification means, okay, you have to be real time, you have to have a big GPU cluster to do that, and you have to choose your taxonomy carefully so that it matches the actual interest of the product. And then you can also do face detection, which is again another problem. So I mean, we have to fit all these problems into a common software stack, and to respect the latency requirements. So yeah, I'm gonna tell you now more about a specific use case we have on live video classification. So I told you earlier about like the need to transform the input distribution into a better output distribution so that it matches people's interest in general, and you can show something that's actually good, and you can at the same time filter the content you want to filter out. So that's what I call the right taxonomy. If you take ImageNet, typically you have a very broad taxonomy and so on, but if it's totally unusable in a product, right? Because it doesn't match what you want exactly. Sometimes you want to actually create clusters of concepts, high-level clusters of concepts, just for the purpose of building a product that's meaningful. So in real life, concepts are a mess. I mean, you have like loose connections between all the concepts or implications and all that kind of stuff. So we see the taxonomy as a huge graph, a huge complex graph, and we want to be able to reflect that into our product. So I'm taking an example here. Like the big oval here you see is like the oval, so it's a 2D space, and we try to represent the actual concept in 3D space. Let's say an animal here is the big oval you have, and then within animal you have like a high-level class that's mammal, and within mammal you have like dog and humans. And you can see that structure is pretty organized because, of course, if you're a dog, then you're a mammal, then you're an animal. So it's pretty simple. You have a hierarchical structure, but sometimes you don't. For example, on some videos, you're going to see the eyes of the dog, but sometimes you won't, right? So this is what we call like some kind of a loosely connected dependency, a loose dependency between dog and eyes. Same for human, right? You're not always going to have, but you cannot factor out eyes when you have a human, or you cannot say, if I have a human, I have eyes, right? And then you have like totally independent labels that live outside the world of mammal, and you can say, okay, they're independent of mammal, but they still relate to animals. So we need to find like a logical and structured way to think about that. And one other thing we want is the taxonomy can be dynamic. So over time, you want to be able to add new concepts. So for example, I want to add seafood. Seafood is a good example because some of the seafood is going to be is going to intersect with the animal space, but some won't, right? So so it's actually, because it could be like, the plate, or kind of stuff could be plastic even. So yeah, I mean, all of that is super important to us and makes it super easy to map on an actual product. If you don't do that, then you're going to spend a lot of time redeploying new models that have been retrained for a long period of time. So what kind of solutions can we use for that? Of course, the first thing is to do multi-leveling. The only thing with that is you have to have, you assume that everything that's not on your image or video is negative, right? It's not there. So every image has to be perfectly labeled, right? With all the labels. So that's a lot of work in terms of leveling first. It's not dynamic, meaning, it can be, but what it means is like when you add a new concept, and that concept is not like completely independent of all the other concepts you have, you have to, even if it is, you have to go over all your samples and relabel them one by one, and like new labels. So you can do that, like you can be tricky about that. You can have like techniques, but it's all handcrafted, and we don't like that because they're lazy. And then what about negative examples? One thing that's important is sometimes when you do active learning, what most social networks or big tech companies do, meaning you have a first model, you predict a range of concepts, and then you have curators that actually say that's true, that's not true, that's true, that's not true. Right? And so you end up with with a lot of examples that are, either like binary true or binary not true. And so, but it's actually super valuable to know that there is not something on an image, right? So we want to also use that and to distinguish negative examples from positive and from loosely dependent examples, right? So one way to do that would be to use actual probabilistic graphical models. That's great because you're able to actually represent any kind of structure between concepts. You can say, hey, okay, I mean, that concept, I don't know about that, so it becomes a latent variable. Then that concept is clearly negative on the image, and that concept is positive, and then you can try in your graphical model to actually output the nice multi-dimensional model. But the thing is, it doesn't scale at all. Why? Because you're doing loopy belief propagation. I don't know if everybody's familiar with that, but it doesn't scale very well, especially over a few hundred examples. It starts to, there is no guarantee about the convergence first, and it can be oscillating. And over a few hundred examples, we noticed experimentally that it's not that great. So one of the solutions is to reflect the taxonomy graph in the targets, like the actual targets you train your model on, dynamically. What I mean by that is we need to define a taxonomy graph. So, yes. So we want to define a set of relationships between concepts. We're limited to inclusion. A belongs to B. That means if I'm A, then I'm B. So if I'm a dog, I'm an animal. Independency, meaning they have nothing in common, these two labels. Like for example, clans and dogs. And you can have a loose dependency, meaning you can have some intersection between your sets. But it's no full inclusion. So, okay, let's say you've specified a set of relationships between all your labels. Then the thing is, you have to propagate the logic of this graph because a lot of relationships are going to be actually inferred from the one you define. That means that okay, you assume everything is independent. Then you have your graph, and then you propagate the relationships between every concept using, the most simple logical rules. Meaning, if A implies B, then and B implies C, then A implies C. Okay, that kind of stuff. If like A implies B, and C and A are loosely dependent, then B and C are loosely dependent. I'm not going to go over the whole thing, but you can do the same with contrapositive statements, meaning, if A implies B, then not B implies not A. All that kind of stuff. So you backpropagate over your graph until it's stable. And next, what you have to do at training time is to do target propagation. That means for each sample you have a certain number of positive labels and a certain number of negative labels, and you want to propagate them according to the taxonomy graph. That means they're all 0 by default, right? And then you're going to use all the rules you've inferred above to say, okay, if A is activated and A implies B, then B is activated, and so on and so forth. And you do then the same kind of propagation for the negative labels, and you end up with an actual target that's very much richer than the original. So, for example, if I take an original target that's dog and garden, so there is a dog and a garden in my image, and there is not a human, propagation means, okay, unknown. So I'm going to propagate the unknown, the unknown taxonomy graph. So what it means is like, I'm going to say, okay, unknown is human and green. That means it's loosely dependent on my input targets. I'm saying that because I can imagine that I've defined dog to be loosely dependent on human, because usually you have always like, verify the two together. So I'm going to say, okay, I'm not going to look at human. Then you have to define the positive, so it's going to be dog, garden, and then you can infer that you can have animal and mammal. So all these two new concepts are going to be activated at runtime. And then negatives means, everything minus the positives and minus the unknown. But the thing is, you know that there is not a human, so you're going to actually get rid of human in unknown. So once you have that new target, which is the one here for negative and that one here for positive, then you can train. So The reason why it's good is you can scale that to thousands of concepts. It's dynamic, you can add concepts on the fly. You can do active learning super smartly because you can train on negative examples. You can also define high-level concepts implied by sub-concepts. So let's say I want to create the mammal concept. I can just say, hey, okay, it's implied by all these examples of mammals, all the possible examples of mammals. And without any training data, the mammal concept is going to be automatically created at runtime. And the way we do that is just a loss function, right? The problem is we are super lazy. We don't want to code a loss function like that, super rigorously with all the backpropagation and stuff because it's a bit annoying. So we use torch autograd. For those who don't know, torch autograd is a package that Twitter Cortex open sourced a while ago that does auto differentiation at runtime. So what I mean by that is that you just write out numerical expressions in torch. Additions, multiplications. I mean, almost all of the expressions you have in torch, indexing, all of that. And then at runtime, the autograd is actually implicitly going to define a compute graph every time you call the function. So the great thing about that is, like some libraries like Tiano and TensorFlow are going to do this ahead of time. So you define your graph. Then it's static, and it's always the same. The good thing with that is every time you call it, you're gonna redefine a new compute graph, which means that you can do super crazy things. Like here, you see, that's my autograd function here, and it has like conditional branching. It has if statement, closures and stuff, and it's natively supported. You don't have to call any crazy module to actually do that. So that's extremely practical for us, especially in that kind of case where we have actually like for loops. We have to look at all the possible targets, propagate the actual activations, and so on. And that's the actual loss function. So just trust me, it works. It's all defined autograd, and the last line, you cannot see it here, but basically we transform that into an actual NN criterion. So for those who are familiar with torch NN, and so it can be embedded in any kind of NN module as well. So yeah, that's the first thing I wanted to tell you about. Then one thing we really focus on is the object localization. Of course, everybody does that. The only problem we have is we can run super complex segmentation models, but it's super slow, and you need to label the actual images pixel-wise, or at least roughly, and that's not what we want to do. So what we're doing for that is we use saliency maps. So we follow that article by Simonian and all. And basically what they do is they do inference plus backpropagation, and they build a saliency map for each concept according to the backpropagated gradients. So the way it works, it's at training time, you train like a fully convolutional net. Why that kind of model? I'm going to tell you that after. You start from 256 by 256. For example, you end up with a 2 by 32 by 32 final map. 2 because you have two predictions, phase versus non-phase. Could be one, just phase. But anyway, then we do spatial averaging, and you get your prediction. So we train on just a binary classifier of phase versus non-phases. We don't do any semantic segmentation at labeling time. So the first step would be to predict, okay, is there a phase? And then we're going to say, okay, there's a phase in that case. And then, the reason why we use fully convolutional nets is that it gives you a nice last map, a final map of 32 by 32. And if you don't have like too many layers and two big kernels, then the dependency of each pixel here, so it's the upsampled last map from 32 by 32 to 256 by 256. The thing it gives you is that you get activations that are kind of localized, right? So you keep some kind of local information. It's not, we can do otherwise, but it's still interesting to see that it works, right? So you see that the great thing with that it kind of matches. But so how would you go from that to an actual prediction on the localization of your object? Well, the way we do it is more like principle. So we do pixels backpropagation like in the original paper. You get something like that. You get like a map of gradients value. You can represent like that, but as you can see, it's super noisy, right? So we have to turn that into something meaningful. So the way we do it is like we take constant convolution, meaning that all the weights are equal to some constant value. And we run that, like we take multiple layers and we run that over that image. And what it gives you is like the actual that high values are going to be reinforced and the actual low values are going to be like thrown off, but in a like kind of crude neighborhood way. So it's not going to be like that pixel is over a threshold and I keep it, and that pixel I don't. It's going to be like, okay, I run these convolutions, I get like kind of maps of values that are like either very high or either very low, and finally I can just cut it, And the way we cut it is just by a simple, like, I mean, we can have multiple ways of doing it. But if you choose your threshold carefully, you end up with a binary map of activations. And as you can see from that, you can just graph cut and get nice bounding box. And if you combine the two, you get like this bounding box plus the actual, like we just put a threshold on the last layer map. And you see that it gives you some kind of relevant result as well. And the thing is, it's already connected. You don't even have to do any kind of processing using convolutions. So yeah, very quickly, why is it good? It's because you use the same model. You don't have to use a new model that's specifically designed for semantic segmentation. It's generic, it's fast, and it's easy to label because you use the same data set. Yes. All right. So, do you have any questions? Thanks.
Saliency map to determine where the face was. Why did you have to go do that map?
You mean? Oh, the last. Why don't we use the last map?
Why don't we use the saliency response to figure out where the face is rather than
I mean, why don't we use that guy instead of the?
Yeah.
Well, the reason is that it works for faces. Because for faces, you don't hit. So what happens here is, let's say you have like 3 layers of 5 by 5 kernels, right? So basically, each pixel here is gonna get information from like 13 by 13 patch of the original image. Yeah. But if you want to do perfect classification and prediction, you need to have information from the whole image, right? Because you can lose context. But for faces, it works. Right? It works super well because it's usually located in the same spot. Okay. But if you want to, you see. So which is why. If we want to predict like, I don't know, like something more conceptual, like parties, stuff like that, we would need to actually do the pixel backpropagation. Yes?
So I think it's very interesting, this concept of having a graph to represent the... but I just wanted to get a feeling, I mean, to do the work that you want to do, how complex do you expect this graph to be? Is it going to have hundreds of nodes, or tens of hundreds, or thousands? Or?
So, I mean, yeah, the way you're going to do it practically, you're going to have like a very large number of individual labels. You don't know a priori if they're like, connected or not. And usually, every time you have a product, you're going to connect the dots, right? And usually, I mean, you're not going to need to connect everything together from scratch, but that's something you can build, every time you have a new kind of request. So, for example, you might imagine that, hey, okay, we would like to filter out content based on like this 100 classes, and then you're going to build like a new node that's actually implied by this guy, right? So that's the easy case, and then at some point we're going to say, okay, well, these two concepts are actually clearly connected, like dependent, but loosely. So okay, we're going to have the graph and see if the performance gets better for that actual prediction. And so it's like very, very incremental.
If the training goes wrong, do you have some way of recovering? So let's say the algorithm links a face to something bad.
Yes.
Pornography, let's say, and you start cutting out all the faces from the images because it just builds this confusion. How do you control this?
Oh, you mean like we're going to say, okay, that's a porn image, so it's positive for face but negative for porn? And
Yeah, I mean, if a link is created that is not necessarily a true link, or it's not always true, but it have bad implications, like, for example, you start eliminating images showing people's face.
Yeah, we could actually trick the models to make it believe that, you know, like, there's no face on porn images, and stuff like that. I mean, you can actually specify that and make it stronger with respect to the rules you want. But I mean, we don't do that for now.
So you mentioned one thing you have here is sort of exclusion links, things that are just incompatible. So you have the example of clams and human idea, but it could have an image that contains clams and humans.
Yes.
So that means, so when you see a human, do you treat clams as a negative or not?
So no, because what's going to happen is they're independent logically. But then, if you label your image with clams and humans, both are going to be activated at training time. So it's just that if you don't specify clams, but just human, by default, clams is going to be at 0. You know, you're going to train with clams being like actually like there's no clam on that image.
So 0 means false. It doesn't mean ignore.
Yeah, exactly. It means false in that case. But if you actually specify that it's a positive, it's going to be taken into account as a positive.
So you're assuming that the labels are complete for an image?
Actually, so true, except that, I mean, partially because you can define this loose dependency that actually allows you to, you know, like say, okay, I don't know, I have partial information only on my data set, then I can just, you know, say these two guys might be connected, my labeling is not perfect, and then I'm going to just ignore them again. Yeah. Thank you.
I think that's all we have time for, so let's thank Nico again.